even more, I think, than other subjects, because things always do go wrong, even more than you expect. It can be a very stressful experience. So I strongly suggest to everyone that if you did actually benefit from getting that last-minute reprieve, then count your lucky stars and think, gee, next time I better arrange things differently. So start it as soon as you get it, I think is the story. Now, I won't talk about it. At the moment, it's in a sort of limbo because there's a couple of students who have extensions for various reasons who are still working on it. And, of course, you're allowed to hand it in late as well with the late penalty. So it'll probably be not till next week that we start talking about it. But the tutors and I will start marking it on Thursday. If you remember, last lecture, we were looking at ADTs. And we were looking at how to implement them in C. And the reason we were doing that is, one, ADTs are important, and two, I realised from talking to you guys that you've come from a range of different courses before coming to this course, run in a range of different sessions. And although in theory 1917 does cover abstraction and ADTs, a lot of you had taken a path where you hadn't seen it. So some of you are hearing this for a second time because you've already covered it in first semester, and some of you aren't hearing it, aren't hearing it at all, and then the ones who aren't here, I guess, and some of you are hearing it for the first time. So what I'll do is I'll finish talking about ADTs today, and we'll finish coding up that example we started last lecture. And then I'm going to put up some links to the videos we shot last year, because some of the videos we talked about ADT in some length. So if things still don't make sense, or you'd like to brush up or just double check your knowledge, go back and look, and there's a whole week and a half of lectures devoted to ADTs last semester. Okay, well, without any further ado, let's start. So we were initially trying to solve the brackets problem. Do you remember the brackets problem? Given three different sorts of brackets, round brackets, curly braces, and square brackets, you could embed these in a string with other characters, and the brackets in the string may well be balanced or they may be not balanced. To be balanced, every opening round bracket has to be shut by a corresponding round bracket, and it has to have a stack-like property that the first round bracket in has to be closed by the last round bracket out, and the first curly bracket in has to be closed by the first curly bracket out, and so does that make sense? Am I saying that right? The first curly brace in has to be matched by the last curly brace out. Sorry, I got it backwards. And that's, of course, what a stack does. It's a first in, first out. No, it's a first in, last out structure, which we call FILO. Okay, so we started coding a solution for the balanced problem on brackets, and we realised that its stack-like aspect probably was a strong indication. Guys over there talking. Shh, 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 shh. It's going to be hard for me to say stack because it's so similar to the word struct. Can I just call them both stucts? And when I say stuct from now on, you disambiguate? Or strack? Yeah. So the strack-like structure of the problem was a good indication to us in solving the problem that maybe we should actually implement and use stracts ourselves. Because, as you have probably intuitively gathered, if not explicitly, when you're solving a problem, it's often really convenient to make the solution map onto the problem as closely as possible. Make the solution look like the problem. So if you have a problem that looks recursive, well then probably expressed recursively, probably your solution is best solved recursively, and so on and so on and so on. So it has it has aspects of a stack, so we will implement a stack. And we then said, well, if we're going to implement a stack, we could just rough and ready code a stack in C using pointers and so on and so on. Or we could make an abstract stack. Oh no, an abstract. Who invented these words? My own personal tormentor. So an abstract stack. So we made an ADT stack, or we started doing that. Why did we want to make it abstract rather than coding a specific one? What's the advantage of having it abstract?
Dependent features, and you can just focus on what it is.
So in terms of thinking about it, it helps us focus just on the main features, which is a really nice...
Stuff like layout.
The other stuff like the implementation and so on, we can defer that till later. So it's a really nice strategy for approaching solving the problem. Lets us focus on the main things first and the minor details later on. Lets us delegate things till later. That's a really good way of managing your brain. I think I've mentioned before, computing's really just about managing your brain. Your brain's smart enough to solve any problem, but only if you break it into bite-sized chunks. And the art of programming is really the trick about working out how to break your problems into bite-sized chunks so you can reassemble them all easily and you have something beautiful rather than a whole lot of bite-sized chunks on the ground. So, yeah, so one advantage is it lets us concentrate on the main properties. What's another advantage of using an ADT to represent a stack? Easy to change. We can swap it out and swap it in with another stack ADT. That's really nice. Why might we want to swap it with another stack? For testing purposes? Yeah, I guess for testing. Like if something's broken, we have a standby we can put in. How would it help us test? You're thinking you check the results using both stacks are the same or something? Use one stack to check the other or something?
No, or like...
this is like the Germans in East Germany, the Stasi or whatever. Yeah, get them all to check each other.
100 people can write test cases and they have like a common interface.
Ah, yeah. Yes, it facilitates testing. That's right. Because the stack has a known interface and everyone's not going off cowboy-like fashion designing their own thing, but we're all being forced to comply with this interface. The interface I've put up there, that's a fancy way of saying we're all forced to implement these functions with these type signatures and specified behavior, though I haven't written the behavior up. That means your test for your stack can be used to test your stack, can be used to test your stack, and your test can be used to test, and that's fantastic. We really like testing other people's stuff. Remember, there's a great advantage to that. If you ever write a system and you're the writer and the tester, that's a really bad design. It's like starring in and directing a movie. You know, has Tom Cruise directed any movies, or Tom Hanks? Anyone whose name begins with Tom? It's just a really bad thing, because the role of the director is to say, actually, your acting sucks, man. Fix it up. But strangely, Tom Hanks never says that to himself. You know, really, you want to have checks and balances. So, yeah, it's a really good idea to facilitate. And it's also, if we can generalize that a little bit more, a really nice way of facilitating group work on a project. If you have well-defined interfaces, everyone has well-defined components that plug together in a well-defined way, then it's easy enough to say you do half and you do half, because we know how their halves are going to fit together. It's not this horrible nightmare at the end of trying to integrate the two. Yeah. So there are all these really nice reasons, in addition to correctness, based around the process of writing software, that means if we can make things abstract, it has all these nice benefits. Sometimes there's a cost, of course. Sometimes there's a tiny little bit more work in dealing with the abstract structure. And you might be tempted to strip some of the abstraction off. You think, oh, I can save one pointer dereference if I don't make it abstract. And, you know, maybe that's okay to do sometimes. If you need to do a billion operations on it, and that's a billion dereferences, and that's just too far, that's just too slow, that's just not going to work. But 9 times out of 10, in addition to that one dereference, you're doing 100 other things, or 1,000 other things. So saving that one dereference would make less than a % difference of speed up to your code. And as I've talked about before, let's not worry about the small stuff. Let the pennies look after themselves. Okay, so here's our stack interface. I can't believe the word interface doesn't have something like ACK inside it. It reminds me of, has anyone seen come down and all they say, now it makes sense. What do they say? You remember they just go ACK, 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 ACK the whole time? The Martians in Mars Attacks, you've got to see it. It's homework. Only so you can empathise with me in trying to say ACK in so many different ways in this lecture. Okay, so we've got something to make a new stack that returns a stack, something that pops an element off the stack, that destructively changes the stack. Okay, this alters the input parameter. And it also gives us the thing we popped off. We've got something that pushes an element onto the stack, and given a stack and an element pushes it on. It doesn't return anything because it alters the thing that's the stack that's passed in, and a test that tells us whether the stack is empty or not. Okay. Now, last lecture I was coding this using my wonderful Xcode IDE here, and I made a duplicate of a file somehow. I think I'd already written a sample version before the lecture just to make sure everything worked, and then I deleted my own code, and then it wouldn't run because it was deleted, and it was a big mess. So I've restored it the best I can, so I hope this matches exactly what we did last time, but if not, that's fine. We're now seeing a slightly different interface. I have a vague recollection that last time our pop altered the stack but didn't return anything. We had a separate function to return something. Is that how we did it? Yeah. So we had a top and a pop, did we? We're just asking for more troubles. I'm glad we combined them. Okay, all right, so here's what we got. Let's implement it. Oh yeah, we did implement it. And remember we did a really crap implementation? I put in a proper new stack. Oh, and you guys suggested we rate the stack as an array. I initially said 10 items. Maybe to make the code nicer, I shouldn't have a magic number. I should call it max stack. Oop. What's the last word? Max stack. Size doesn't sound like ack, though. Is there a word that means size that has ack in it? Black. If anyone can think of it, we'll change this later on. At the moment, we'll call it max stack size, but it doesn't seem right, does it? Has to find max stack size. And let's say that's 100. Well, you can make it however big you want. Oh, classic blunder, number 1. What could I have done there? Semicolon. I could have been tempted to put a semicolon there, and I hope you all have done this. And what's that? What's that? Not only don't you have to do it, you shouldn't put it. Because wherever the word max stack size, which is just too easy to say, appears, the pre-compiler is literally going to replace it with whatever's here. So it would stick in 100 semicolon. That would just cause all sorts of confusion. So yeah, don't put your semicolons there or you'll get weird messages. Okay, so we've got, we made a type. What have I done? Oh, I've left it there. How could I have done that? Okay, so here's our way of making a new stack. We malloc the size of the stack, make that many bytes. We assert that what we're getting back isn't null. How would we get something null back? If we're out of memory and the malloc fails. That's how malloc communicates failure. I guess that makes sense. It communicates it in the data stream it returns, which is an odd way of doing it, but I guess that makes sense in C. It returns null to mean it wasn't able to do what we asked it. And then it returns it. So that new stack looks okay. Shh, shh, shh. Now, guys over there, what's happening? Ah, it's Chris. Chris, shut up, man. I know your name. And it is Chris, isn't it? No, damn. Is it Mac? Mac. That's Mac. Okay. So Mac, shh, shh. I'm going to call you Black Mac. Okay? And I'd like you to be quiet. Okay? Because otherwise I'll have an attack. And my mind will crack. Rap computing, man. Okay, so we implemented that function fine, but look, pop, what does pop do? It doesn't alter the stack at all and always returns the letter C. That's fine if there was a C on top of the stack, but gee, it's not correct if there wasn't. Push, you give it something to push on, an element, and what does it do? Nothing, it does nothing. It says, yeah, sure. That's right, I've implemented what we call a stub. This is basically the smallest implementation I could type in. It's clearly incorrect. Is empty, has to return true or false, and it always returns 42. That doesn't make any sense at all. So nothing makes sense. Why did I write it really quickly and crappily like that? Because what am I rushing to do? What do I want to do? I want to try and compile it. Why do I want to try and compile it? So I can test it. So what do I want to do first? No. What's that? Jack. Write some test cases. Well done. Okay. So we're going to write some test cases. What's the name of our file that we're going to put the test cases in? Test. I'm writing test for my stack ADT. So what am I going to call the file? Test stack. Okay, let's go. So we make a new file. It's a C file. Yes, please. Called test stack. And we'll make a .h file and we'll say it's going to be for the test stack executable. Finish. I better tell it that we're interested in test stack. All right, so now we've made test stack. Let's just check that it works. Int main, what is it? Int argc char, what's that? I'm in the .h. Oh, thank you. Don't need a .h for my test file. I need the .c. Thank you very much. My test stack isn't going to have a .h. let's do it. I'm going to do a deletion because I just love deleting files in an IDE. I find that leads to enormous happiness. So let's just... Oh man, let's just go all the way. Okay, it's gone. So we've passed in the argument counter. Now we're going to pass in the command line arguments, and they're called what? Arg. Oh yeah, star. Thanks. It's a pointer too because it's a string. Arg values, and there's an array of them. And now we are done, and we're going to return exit failure. It's making a predictive text inclusion. Okay, and now if I want to return exit success, I better include the file that tells me what that means. stdlib.h. And what else? I might want to hash include stdio, because I'm just about to print something out. And what am I going to print out? What do I print just before I terminate? What's that? I haven't put any asserts in yet, but yes, you're right. I'm going to need to do that very soon. Let's just have a quick pause to think about that. Well, at uni we're on strike, but because we're teachers, we can't actually ever properly be on strike. It's like doctors. So we amortise the strike over the whole year. So, yeah. So all tests passed. Jack. Okay. No. Here we go. Are we ready? Go. Woohoo! And let's have a look and see if it ran. See what the output looked like. All tests passed. We're in. Shh, 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 shh. Okay. So now we've got our testing structure set up, and the whole thing compiles and everything hangs together. What's the first thing I'm going to do? Before I even write a function, I'm going to write a test. Which function should we do first? Well, I've already written one of the functions. Why don't I write a test for that? What function did I write already? Shh, 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 shh. Guys, there's just constant talking over there. I'm moving my desk over there, so I'm near you. Or have this dilemma that I sort of want to rotate the whole hall. I want, like, you guys to all shift along 10 and the last 10 there to rotate and come around here. What's a fast way of rotating something? If suppose this was an array, this first aisle here of seats, this is an array of, say, 20 places. Say it's got 10 on each side. And I wanted to shift it along by 10. Oh, that's quite a lot. I wanted to shift it along by k, say. How would I do that? But I could just sort it until it's right. That's right. That's a very beautiful answer to that problem. Suppose, though, we wanted another one. Because that would be slack, to use Bogo sort. So how are we going to do it? Guys, tell me, quick, design an algorithm. We want to move things along. How do I move things along in an array? What? You're just calling out random words now. How do you do it? What's that? Barrel roll. Yes! Copy the first one to the end, but then the end's overwritten. Shh, 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 shh.
Extend the array. Copy the first k at the end. Like
oh, extend the array. Oh. Oh, I see, yes. So, two questions. One is, we could just make the array longer and redefine where start and begin is. So we could just operate on our indexes going into the array, essentially. That's quite a nice idea. We need to have it abstracted to be able to do that, but that's a very clever idea. Leave the array exactly as it is, and when people access elements in the future, do an operation on the index they're requesting. They ask for 7, think, oh, they really mean 5, and give them 5, and then we didn't have to move anything. That's very, very clever. But your question is, of course, right to the point, which is, how much memory do we have? If we have a linear amount of memory, spare memory, we could just copy the chunk, the guy that's about to be moved into the temporary memory, shuffle everyone else along, not one at a time, copy them all into the right spot, and then copy that big chunk to the other end. but that would need linear extra memory. What if we didn't have linear extra memory? What if we wanted to do it in place or with a very small amount of extra memory? Rearrange pointers? No, it's an array, so there are no pointers. An array, the elements are stored one after each other. If it was a list, yeah, we could do it. If it was a list, it'd be easy peasy, wouldn't it? Problem with arrays. Both the strength and weaknesses of arrays is everyone's jam-packed next to each other. The strength of that is you don't have to do any complex operation to find the next guy. You can compute exactly where he should be. The disadvantage of that is if you want to move someone, you can't just change a reference to them. You've actually got to physically move them. Okay, well, that's an interesting question. We might just leave that question there for a bit and return to the lecture. So we're going to test our first function. So we're going to write a function called test. What was our first function? Was it new stack? Is that what we called it? New stack. Test new stack, please. And we're going to need to put the prototype for that up somewhere. All right, now let's implement the function. Let's write a test. What's a decent test for new stack? How are we going to test that new stack worked? Assert what? So assert the new stack is not equal to null because why? Because what would null tell us? That it failed.
No stack. It'll tell you that it's not being allocated at least.
What's that?
No stack exists.
It'll tell you no stack exists. Why is that?
Yeah, because it's null when you pass it. If the stack exists when you pass it into the function will not return null.
I wonder, is everyone listening to these answers? Can everyone hear these answers? Let me repeat them. Shh, 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 shh. If you are just sitting here this lecture passively and you're thinking, oh, he's just going to code and occasionally I'll look up and see what he's coding and he asks rhetorical questions and I'll just sort of ignore them. You'll miss the main game because the main game isn't the code I'm writing. The main game is the idea of ADTs. There's someone over there still talking. It's not you again. Man, that's it. I'm going to leave. I'm going to take my coat off. Shh, 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 shh. And you don't want to see what's under here. I had to cut the... it's just horrific. Okay, so you've got to pay attention. Even when I'm saying pay attention, you've got to pay attention. Okay, that's a trick. So, yes, the question was, for me, how do we test that a new stack's work? The answer was we could test to see if it was null. I screwed up my face when someone said that. And I said, why? And they said, oh, because if it was null, memory allocation. So, why did I screw my face up? Why am I not completely happy? It's not a bad test. We're probably going to test for it, but let's make sure we're testing for it for the right reasons. Yes?
There's actually nothing to test for null. Like, I can't see anything there to test for null in that function.
You can't test for null? Well, I mean, you could...
test nothing for, like, there's no variables or anything.
I haven't created any variables, but I could create a temporary variable. I could do this. I could do this. Let's suppose I'm going to do this. Stack, new stack equals new stack. Assert new is not equal to null. Now, that's an okay test, but it skirts close to not being an okay test. So I want to make sure you understand why. Yes?
Doesn't malloc return null if it fails?
Malloc returns null if it fails. Yes? So you think I should test to see if it's equal to null?
Yeah. And that would give you, like, it has failed in creating a new stack.
No, when I do an assert, I say what I hope to be true. And if that is not true, then we get an error. So I hope that new isn't null. So does that right? I think you just got it backwards. Yeah, yeah.
Why you returns an address but it's not pointing to a stack?
Shh, shh, shh. What if it returns an address that's not pointing to a stack? Yes, in the sense the test isn't sufficient. Merely not being null won't be enough to tell us anything. Yes?
Would it be better just to try and do something with your stack? I mean, the program might return nulls for a valid reason.
What's your name? Sam. I've asked you that before, haven't I? Is this the second time you answered a question? You think it's the first? Okay. In my dreams you asked it a question. It was very clever. But this one even beats that one. Yes, Sam's question's spot on. answer is spot on. Is this type stack a normal type? As far as C is concerned, it is. It just looks like any other type. But as far as we're concerned, we have a mental model of what this type is. What is this type? What am I going to call it? It's an ADT. What does the, I'll start easy, a T stand for? Type. The D? Data. What about the A? Abstract. That's the key thing. It's got to be completely abstract. What do we mean by abstract? We're not actually allowed to know how it's implemented. We're not allowed to know anything about it. We can't know zip about its underlying type structure. However, because of the way we implement them in C, it's actually really important to know that it is a pointer to something. So we know our ADT is a pointer to something. So it's actually valid to check we're not getting a null back because we know it's a pointer. C leaks that information, and we need to know that in C to know how it behaves on passing into functions, whether it's by reference or copy. But normally, this sort of test is just right out of the question. We cannot compare the result we get from a function with what we think it should look like because we're not allowed to know what it looks like. We are allowed to know it's a pointer, so we're okay. So what Sam said is spot on. The only way we can test a stack function, because we can't know underlying, like, you speak Netsilik Eskimo. I'm not allowed to know anything about Netsilik Eskimo. You are an interface function to something. You are, you can tell me my student ID, right? This is some abstract type here that's capable of telling people student's ID. And given a student ID, you can tell me the name of that student. Given a name, you tell me the student ID. Given the student ID, you tell me a name. However, all student IDs are in Netsilik. So I say to you, my name is Richard, what's my student number?
51.
No, in Netsilik. It's got lots of guttural sounds in it and fish and things. That's what he says. Now, I don't know if that's right or not. My student number is 51. I don't know how you knew that. That was a bit freaky. You're not that guy outside our window at night. So our student number is 51, but how do I know if that's Netsilik for 51? Well, I could look it up. In the Second World War, they used Navajo Indians on the radio transmissions. The Americans did sometimes, just relying on the fact that the Germans couldn't speak Navajo. It was a fairly small unknown language, so they didn't have to encode it. They just got Navajo speakers to speak. But I can't test. Fish is 51. There's no way of me telling if it's 51 or not unless I get a dictionary. And there's no point in me getting a dictionary because you're completely abstract and student numbers have been completely abstracted, and maybe tomorrow they'll decide it's cheaper to employ... who's cheaper? They're going to employ someone really... Yaks. They're going to employ yaks. And you'll answer me in yak speak. So I can't have a test saying it says this because maybe you'll answer me in yak. The only thing I can test is the functions all have to be consistent with each other. So the only way I can test you give me the right answer is what? Feed it back in. So I could go, what's my student number? My name is Richard. You've got to say it now.
Say what?
Say it in Netsilik or in Yak. No, you've got to say my student number.
51.
Okay, all right. Because in Netsilik Eskimo, 51 means 57. And that's actually my new student number. I was tricking the other time. So, all right. So I say, I get from you, what's my student number? You say, I don't understand what it means. I can't test that you've said the right thing. But instead, I don't need to. Because instead I go, what's the name of the student with student number? And you go, Richard. So pairing functions together like that, we can test that the right thing's happening, even though the data that's moving between them has been abstracted. Does that make sense? Does it make sense? I've put you on the spot. But well done, you did very well. And I didn't really expect you to know Netsilik. Okay, so if I wanted to test that new stack work, well, before I do any operation on any stack, I really should check that it's not null. Because if it is null, the whole thing's just not going to work. But I might leave that pain of checking to see that stacks are not null. I might actually leave that to the functions that deal with stacks, the interface functions. I don't think either user have to worry about that. So the only way I know of testing that new stack has returned a new stack is to what? is to assert, what's that?
Is empty. The function.
Use is empty, that's right. That's right. So I could say assert is empty new stack. Now that's a legal test, and that should clearly be true. Does that make sense? Oh, is it called new stack or new? Oh, I've already done it. Yeah, let's just do it like that. Oh, yes, thank you very much. New stack. Does new stack return a stack? New stack returns a stack.
But then you're memory leaking it nowhere. You're not destroying it ever.
Oh, yeah, I've got to kill it at the end. That's right. Thank you very much. Well, it's my testing function, but you're right. I could have a million tests.
And you might
Yeah.
leave it in your program.
Yes, I might have a million tests and I might leave the tests in there. Thanks. Yes, that's right. So let's go stack new equals new stack. And at the end, I've got to somehow destroy the stack. Okay. Is everyone cool with that? Is that going to work when I run it? Let's have a look. Oh, got some errors. Stack undeclared. Oh, it doesn't know about stacks. How can I tell it about stacks? Hash include stack.h. What else do I need to hash include? Someone called it up before? Yes.
Also, we suggest running the bracket tester on this program.
Oh, yeah. A more elaborate way of testing it would be once I've written specific tests for every function, I could then embed this stack in some environment where it's used a lot and check that the environment is happy with it. And what Theo was suggesting... No.
I had a missing bracket.
Oh. I had a missing bracket? Had a missing... Oh, well, I'll find that. Okay. This is... I see. But what I thought Theo was saying was actually a good point, which is if I've got some piece of code that really relies on stacks to do its job and gives stacks a good workout, and I have tests to check if that piece of code is doing the right stuff, then I might as well run it with this implementation of stack, and that would be one good way of testing it. But first I want to test each function just primitively. So warning, unused variable new, I'm not using it, is empty, oh yes, is empty new. And, oh thank you, I've got an extra bracket. See how it goes now. All right, it's happy, it ran. Let's look at the results. All tests passed. Woohoo, it worked. But hang on, it shouldn't have worked, should it? How come it worked? Why did it work? I haven't even implemented these functions, yet it's working. Can anyone tell me why it worked? I didn't save it? No, I didn't delete it. 42 is the answer. That's right. New stack always returns 42. Now, that means new stack's always returning true because non-zero is true in C. If a dummy implementation can fool the test, what does that tell you about your test? It's not a very good test. It's not perhaps ruthless enough yet. So I not only want to test that a new stack is empty, well, I reckon I've probably tested new stack all right at the moment, but I haven't really tested is empty very well, have I? So maybe I should write a test for is empty. I should be destroying the stack. I am going to have a memory leak, but I'm not going to destroy it at the moment because I haven't got a destroy function built into the ADT interface. So, yeah. So I'll just leave that out for the moment. So, how am I going to test is empty? Can anyone think of a good idea? I want to know if the isEmpty function does the right thing. What's that? I've got to push something on the stack. At the moment, I'm only testing the case when the stack is empty. You've got to make sure in your tests that at least every possible combination of flow controls through the program is explored and exercised by the testers. So isEmpty can return one of two possible values. I better check at the very least one test for each of those values. So let's push something onto the stack. So let's get a new stack, and then let's push, what are we going to push onto the stack?
42.
Push 42, no, it's a stack of characters. And let's have a look at the interface. What do I push? I push the element first and the stack comes second. Okay, so I'm going to push 4. I could push 4 onto the stack. And then I could push 2 onto the stack. And now does the stack contain 42? Or does it contain 24? Okay, now assert not is empty. It ran, all tests passed. What? Oh, I didn't call test is empty. So how do I know what tests are being called? Here it silently failed without me noticing. I didn't notice that I didn't call the test. That's terrible. You don't want me to rely, you don't want this testing thing only to work if I notice stuff, because that's the very thing I'm trying to defend against, me not noticing stuff. So what should I have done? I should have printed what tests I'm entering into. So yeah, let's say that. Printf about testing new stack. And what should I do at the end when the test works? Okay, and then I better call it. So it actually does get exercised. Guesses. Okay, let's build and go. Ba-ba-bum. Oh, here we go. Oh, well, let's just have a little pause to think about that. Assertion failed. Function test is empty. Is empty new? Aha, not is empty new failed. So it must still be empty. So that tells us what? Either is empty functions wrong or our push functions wrong. Well, I didn't put void. Where didn't I put void? Oh, it doesn't have void in it. Thank you very much. If I leave it out, that's okay. I'm not passing parameters in, but if I put void in there, it turns on parameter type checking and C gets then cross if the number of parameters don't match. So it's a nice way of enforcing that it can't have any arguments. So it's good documentation. Did I put it down here? No, I didn't. Okay, cool. All right, so this tells us, now this is how we're going to do it. This is called testing driven development. So now we're going to go, oh, bugger, one of my tests failed. I better go and check it. Oh, it's push that failed. Oh, is empty failed. Let me write the proper is empty first. How am I going to be able to tell if the stack is empty or not? Let's look at my stack. My stack is an array of characters. How am I going to know if it's empty? There's sort of two approaches we could take. One is we could mix some control information in with the data. Maybe I could have a special character that means empty. That still leaves me 255 characters that I can use, stick in the array. It's no small thing to ask the users of this function to avoid one of the characters, surely, because I need it for control purposes. But mixing control and data flow is just very problematic. It's just a poor design feature. It's a crappy thing to do. Better if your control information exists independently of your data. So I'm storing the data in this type, in the struct, but what else should I be storing? Some control information. What control information should I be storing? Int item count. That sounds good. Okay. Now, as soon as I change the struct, I better change my new stack. I mallocked it. Looks like a bit of a mess at the moment. I mallocked it but didn't do anything. What should I do after I've created this guy? I should say, oh, thank you very much. I should say, new item count equals what? 0. Okay, cool. And now that's easy. Is empty just returns stack item count is equal to 0. What's that? Is empty means it's got 0 items. What am I returning? What, have I made a mistake? I've just confused everyone. What if I put more brackets in? Because it's not very good to have so few brackets. Stack item count is a field in the stack struct. It keeps track of how many items are in the array. And the stack is empty when there are 0 items in it. So what I've done, if I just go back to the top here, my stack was initially just going to be an array of characters because I was pushing characters onto it. But now we realise we need to know some more information. We, the implementers of stack, we, the people on the inside of the stack interface, we need to know how many things are currently on the stack. Otherwise, we don't know how to interpret this data. Some of it might be data on the stack and some might just be rubbish or uninitialized things. So we are going to also keep track of how many items are on the stack. And every time someone adds something to the stack, not only are we going to put it into the array, but what are we going to do? Increase the item count. And every time someone takes something off the stack, what are we going to do? Decrease the item count. Yeah. So our test to see if it's empty is simply to look at the item count. And if there are 0 items in the stack, that's our notion of empty. And the arrow here just dereferences the stacks. The stack's a struct, and it's got 2 fields. One of them's called item count. So the arrow just, because it's a pointer to one of, stack is a pointer, sorry, to a struct. So arrow item count just gives you the field called item count. Is that cool? Okay. So now we've got is empty working fine. Let's also get push working better. How are we going to push something onto the stack? You know what we should do here? This thing you raised before. Assert stack not equal to null. Before we do any operation on a pointer and dereference a pointer, we should always check it's not null. That's just good housekeeping.
Are we allowed to say assert stack, but it's not that?
No, you can't assert stack. Because then you'd be a hacker. Because assert stack is saying, well, you mean assert not stack or something? No, assert not stack. Oh, yeah, assert stack. That's right. The trick we're talking... what's your name? Tim. The trick Tim's saying here is we could just assert stack because stack is a pointer. It'll get evaluated, and C's not fussy about Boolean types. It's prepared to regard anything as a Boolean type, really. It'll cast that into an int. And if the pointer is 0, it'll be 0, which is false. And if the pointer's non-zero, it'll map to something that we regard as being true, because C regards as being true. So saying assert stack is sort of shorthand for saying assert stack is not equal to 0. However, we don't like doing this. Though it's a C idiom and people do it all the time in C. Why don't we like doing it?
I can think of a really bad reason.
Hit me with a reason.
If you just assert stack like that and then they pass in null, it will actually say assertion failed, stack.
Oh, it doesn't give a very good assert error message.
What does that mean?
Yeah. Yeah, okay, but we'd find it when we looked in the code. But there's a more profound reason. That it is certainly would be a very cryptic error message. And I guess that also means it's cryptic to human beings looking at it. Though if you understand the C idiom, it's okay. But certainly not equal to null is closer to the idiom. But no, there's another reason. What's the other reason? Yes? Null might not be 0. Yeah. Null's a pointer. True's an int. So on most systems, I don't know, I've never heard of anyone implementing C, so null's not a pointer. Null's not a pointer to 0. But gee, it doesn't have to be. I'm sure it's not in the standard. And even if it was, it's a pointer. It's not an int. So don't just cast one thing into another thing. If I'm interested in a Boolean, I want to see a Boolean. If I'm interested in a pointer, I want to see a pointer. I don't want you just magically turning your pointers into Boolean because it happens to work in that particular instance. That's just like, it's sort of lazy. It saves you time when you're typing. It looks clever when you're typing. It might save the computer a billionth of a second when it's running. But at the cost of now, your types are all jumbled. So C is not a type strict language. C will forgive you for getting your types jumbled up. But just for your own thinking straight, make them equal. Make the types equal the types. And if something's expecting an int that's representing a bool, because C doesn't have a bool, give it an int that represents a bool. So either give it a true or a false that you've hashed defined yourself, or the result of a Boolean evaluation. You can get all sorts of tricky problems once you start regarding random things as being Booleans, largely because if you ever have to test that things are true or equal, it's quite possible. In fact, it's quite possible for two things to both be true but not equal because any non-zero number is equal. So anyway, just cutting a long story short, make your bools be bools, make your ints be ints, make your points be pointers. Pointers be pointers. Yeah, so you could write this, but I don't want you to. I want you to say it's not equal to null. And let the compiler sort it out and optimize it. So you could even say this. This will probably work because null will probably be 0. But if ever null was hash defined to be something else, that's why it's a hash define. It can be whatever they want. That's going to fail in a terrible way. But also it's just not clear. So while stack is not equal to null, da-dun, 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 and this is sort of communicating we know that stacks are pointed to something, so on, so on, so on, so on. Okay, so is empties looking cool? Oh, and Tim, did that sort of answer your question? It would work fine. I can't think of a single time it wouldn't work.
Okay.
But it's...
Yeah, on an embedded system, you're more likely to access the beginning of memory, and then it might not be null at 0.
But
and you'd be running in C.
on an embedded system, yeah, normally they map the whole page as not mappable, don't they, to catch null pointer dereferences on big systems. But maybe on a small chip, they actually use something at 0, and they don't want nulls to be 0. Yeah. Maybe. Yeah. Because, of course, your null, if that makes sense to everyone, null has to be a pointer to an area of memory that malloc couldn't return. Otherwise, you're in trouble. Otherwise, if malloc returns an area of memory for you and it's giving you 0 and your operating system regards 0 as null, then after you've tested to see if malloc worked or not, you're asserting it's not equal to 0 and actually gave you a pointer to location 0. Yeah. What's that? It's a waste of 1 byte. That's right. It is. It is a waste of 1 byte. But there's no reason... there's no reason... I mean, it's up to the compiler how it deals with the whole null problem. Yeah. It's really a compiler-based thing. Let's not us make decisions about how the compiler's going to deal with it. Let's just treat things as they are rather than as something else that we think will get magically converted to the first thing. No, null's not an abstract type. Null's a pointer. Yeah. Null's not an abstract type, but using null to stand for 0 is certainly abstraction, but it's not an abstract data type. ADT has a specific meaning, but yes, it is an example of abstraction. We're trying not to deal with 0, we're trying to deal with something that represents 0 in a more general way. That represents a null pointer in a more general way. Rather than having to know its details, we just want to know the fact that it's the null pointer. Okay, so we want to we want to push something onto our thing. So what are we going to do? Well, let's first of all, let's assert that our stack isn't null, because we're just about to dereference it. Now, what am I going to do to push it on? How do I push onto a stack? Yeah, Tim, you're doing all the work. I'm just concerned. I had this theory the other day that we were doing too much talking and not enough coding, and we needed to do more coding in the lecture. So we're sitting down doing this painful, slow coding. And I could have written the code and just shown you, and we could have talked through it. But I thought, no, let's actually go through the process of coding. But it only works if we all go through the process. Otherwise, I might as well just show you the file at the end. So I want everyone to be trying to do it. So I'm now just going to, whoever's name is written on this key is going to have to answer the next question. Okay, and the next question is, how are we going to add something to a stack? Is there anyone here called Lockwood? So my plan didn't work. Okay. Is there anyone here who wished they were called Lockwood? Or Lockie? Lachlan? Edward? Oh, Lachlan. Okay. Shoot. What's the process? If I want to push something onto the stack, what am I going to have to do? Remember, our stack is an array of characters. It's an int telling us how many things are on the stack. Someone's just given you a character. What are you going to do?
We have to make our node.
Yes?
And then point that node to null.
But it's an array, remember? Yeah, so we're not doing it as a linked list. It's just an array. So it's even easier than that. That's dead right if we're using a list.
Make the node and then put it in the first.
So put it in the first place. That's right. Well, when we did this malloc here, it set aside enough memory to create a myStack. And here's a myStack. Let's look at what a myStack is. It's a struct that contains an integer and max stack size items. Max stack size chars. Everyone listen to this. An integer will probably take up how many bytes? 4. It's probably taken up 4, so it's probably requested 4 bytes for that. How many bytes has it requested for this? 100. Because each character is probably 1 byte, so it's probably requested 100 of them, unless it does funny alignment things. But if it's packing everything in nice and tight, it'll have requested 104 bytes. Or we could even find out. How could we do that? We could say, yeah, print out. Let's do that in our test code. Just out of interest, let's go, oh, I can't do it in the test code. I can't do it here. Here's where I want to do it. I can't do it in the function that lives outside the ADT that uses the ADT, because the question I want answered is, how does the ADT internally use memory? Why can't I do it? You're laughing. You see the problem. What is the problem? The problem is, it's abstract. I'm not allowed to know how it uses memory. So from the outside, I can't see that struct, so I can't ask how big it is. The only place it can see that struct's on the inside. So let's go to the other file, the stack file. It can see the struct. It's not abstract here. And let's say, I don't know, every time we do a new stack, why don't we print it out? Printf, just for a laugh, size equals, it'll just tell us this, we'll pull it out in a second. Size equals whatever it is. And let's say size of, tell me the size of new. Size of, yeah, new's a pointer, so it'll be new star. Or size of my stack, maybe. Here we go. Let's watch it. Running printf. Oh, I didn't know about printf. Curses. stdio.h. There, that'll tell you. Now let's see, where's our execution here? Just for a laugh, the size is 104. Aha, so it was 104. So it knew it was 104. We then crashed because the rest of our code actually isn't working at the moment. But printed out 104. So going back to what Lachlan was saying. So at the instant we run new stack, it puts aside some memory for us with malloc. It puts aside 104 bytes. That's exactly big enough to hold a stack. We're not allowed to know that from the outside. We just know we've got to point it to this area. But if we were allowed to see it was a pointer to what? It's a pointer to 104 bytes, all sitting next to each other. And that 104 bytes is probably, the first 4 bytes contains the size of the thing, it's a number. And the next 100 bytes contains a whole lot of characters. So we don't have to create any new memory because that happened at the instant of the thing. But the steps Lachlan gave are exactly right, which is we have to stick the value into that area of memory. So let's do that. Let's kill R just for laugh. Don't need that anymore. Where's push? Did I just miss that? New stack, pop, push. Here we are. So it's not equal to null, so we're going to stick the element. Where's the element going to go? Stack dot, what are they called? Items? I should call it item. Yeah, that's a naming thing. That's a problem, isn't it? I should have called it item. Hey, I did. It's always confusing for me as to whether you name arrays plurally or singularly. It depends how I mainly use them. If I'm just passing them around all the time, I want to give them a plural name. But if I'm inside them looking at an element at a time, I want to give it the singular name. It's hard. do whatever's clearest when you're doing it. So let's look at the particular item, and we're going to, whatever item it is, it's going to inherit this new element. We're going to copy the element into it. Item count. So if we've got 0 things, it's going to put it into the 0th place. If it's got 1 thing already, it'll put it into place 1, index 1, and so on and so on and so on. That works nicely. And at the end, we'd better what? Yeah, thank you. That's stack item count. Okay, that's a sort of a push. I'm not terribly happy with it, but let's pretend we are. Let's have a look. Woohoo, all tests passed. Woohoo! So it looks like everything's working. Well, if everything's working, what could I do? I could write, I could just go nuts with my test stack. Have I got a test new stack? Test is empty. Let's have a test push. I hope everyone saw the problem with the code. Don't call it out though. Let me write this near the other code so you can keep staring at the wonderful problem while you're thinking about it. Test new stack, test is empty. Oh no, you can't see it because it's in the other file. All right. Test push. How are we going to test our push function? Well, first of all, let's create a stack, I guess. Stack new equals new stack. Don't forget to delete this at the end. So we've got our new stack, and then we're going to for int. Thank you. Yeah, but I should print out what I'm about to do. Okay, for int I equals 0, I'm just going to I is less than 10, I plus plus. I'm just going to push stuff onto the stack. Push, what am I going to push on? Push, oh yeah, I've got to convert I to an, oh I see, just push it on as a character. Convert my inst to chars. Okay. Char C equals 0. Well, let's start off with C equals A. C is less than J. C plus plus. Push C onto the stack. Oh, thank you. The stack's called new, not called stack. Or in this one, I guess we're not testing the new function, so it's newness, isn't it? Important attribute. Its important attribute is that it's a stack. Okay, what do you think of that? We've pushed 10 things onto it, or however many we pushed on. Now I'm going to assert something. What am I going to assert? Assert. Well, how can I access num items? I can't get to them. I could go assert stack num items equals 10. Is that going to work? Let's have a look. It's going to go, what? Dereferencing pointer to incomplete type. Why is that type incomplete? It's called item count? Oh, it's not called num items. Okay. Let's try again, this time for sure. Dereferencing pointer to incomplete type. It does it again.
Did you already define struct stack, so you can't say it's called variable stack?
Oh, I can overload the word, but all right, maybe it doesn't like the word. Maybe I'll call it my test stack. my test stack. Push? Push? Why are you saying push? Oh, thank you. My test stack. Right, there we go. What's that? Oh. What's that? Yes, that's right. I'm not supposed to know the structure. I can't know the structure. It's complaining because it's saying, what? It's a pointer to an incomplete type. It's saying, I don't know what you're talking about, man. You're giving me this stack. It's not a complete type. It's incomplete. And I'm saying, no, it's not incomplete. It's complete. Look, I told you, you've hash included its definition. So you've hash included stack.h. See? And if you look in stack.h, see, you'll see what type it is. It's not incomplete. It's a pointer to a struct. Oh. Unfortunately, I can't tell you what's in the struct. It's a secret. I could tell you, but then I'd have to... Yeah. Okay, so you get the idea. It can't see what's inside. The only people that know what's inside that struct is defined in stack.c, right up the top. No one else hash includes stack.c. They only include stack.h. So no one else can see anything about it except that it's a pointer. So they can't access item count. So we can't test item count directly. But I could test that it's not null. What do you think? Assert test. Assert not is empty my test stack. And I could assert that it was empty at the beginning. And I guess I could pop things off one at a time and check it's not empty until the very end. Oh, did it pass the test? Oh yeah, it did. Awesome. That's just all the tests passed. Woohoo, looking good. It's still saying he's empty? I didn't test is empty. Oh yeah, that's not good. Test is empty, test push. Testing push. And testing is empty. And testing new stack. Okay, go. Let's have a look. Test is empty, test push, all tests pass. Woohoo! What can I do now to break it? By the way, I really want to break it. I'm just itching to break it. Yeah, I'm going to push lots of items onto it. Let's push... does anyone know the ASCII uppercase letters come first or the ASCII lowercase letters come first? Uppercase come first, followed immediately by lowercase? Then some rubbish in the middle. All right, let's just... Oh, that's not enough. All right, I'm going to go from character 0 up to character 255. Let's go. Whoa, GDB, woohoo, what did I get? It was in the middle of testing push. Thank heavens we printed that message out, that tells us where we were, and now something went wrong. There's absolutely no warranty for GDB. It's actually told me what line the thing crashed on here. I tried to allocate the element to the array, and it's crashed. That's very interesting. Let's do a bit of debugging here. Let's print out about to insert stack up sent D. Let's print it out, the ASCII code for it. So I'll print it out as a decimal, as an int, rather than as a character. And what am I putting in? Element. So all right, that looks good. Print and go. Yes, go. Oh, look what, it's inserting a whole lot of stuff. Oh, it's not crashing. Isn't that weird? It crashed a second ago. And now it's not crashing. Oh. Isn't that strange? Wow. Yeah. So it never exceeds because I cast it. Will this eventually, let's see where it's... about to do something. Oh. So while that chainsaw of happiness is rotating there, what? Oh, it's gone again? Off it goes, and we're off. What's the problem I've got eventually? What problem am I eventually going to get? We better stop it. I'm trying to get a seg fault. Shh. What's going to give me the seg fault? Yeah, I increase the item count each time and just stick it in. But how big was that array that I set up initially? It could take 100 elements. Here I'm putting in more than 100 things. So I'd better put something in my push to check that we're not about to overflow. What did I call it? Okay, so now I'm feeling a bit happier. So I've got a decent push going now. I'm going to put in a pop. How do I... oh, and I better remember what pop does. Pop pulls something off the stack. Oh, does everyone see what I just did then, by the way? Was it clear enough while I was doing it? I just put in a quick check to make sure we're not just about to overflow the array before we wrote. Should we make sure it's bigger than... What's bigger than 0? Oh, assert that the item count is greater than 0. Yeah, there's no harm with doing that. Yeah, it can go negative. Okay. Okay, so yeah, let's check it's in a legal range. Notice I'm doing all these sort of housekeeping checks inside the implementation. So the people on the outside get this check done whether they remember to do it or not. We can't trust them to always run checks. We might as well run it for them. Okay, so is empty's fine, push is fine, and let's write a pop. So pop is going to reduce the stack by size 1. How do we reduce the stack? Assert the stack is not null. How do I reduce the size of the stack by 1? Yeah, I better assert that item count is not... You're one step ahead of me. My next diabolical glee has been removed. Assert item count is greater than 0. Because we certainly can't pop off an empty stack. And then we're going to say item stack item count is reduced. And what am I going to return? Stack. Yep. Items. Stack. Thank you. Now, is it +1? I don't think it is. I think, because C starts its arrays counting from 0, it's just a really convenient thing. It so often saves us having to do a +1 or -1 when we don't want. Okay, thank you. Let's take a little pause to reflect on that. Does that look correct? Yes, it does. Woohoo! Okay, now we stop writing our tests. Let's finish our tests. That was a pretty crappy test that I put in there. If I want to test push, what really do I need to combine with push to test a push? I need to combine it with a pop. So what I really should do is push A onto the stack, and then better assert that it's not empty. Where are we? did you go? Oh, I just shrunk you away. All right, and push A onto the stack. Assert that the stack is not empty. And then assert pop of the stack equals A. And then we better assert the stack is empty. So let's push it onto the stack. Let's check now we've got a non-empty stack. Let's take it off the stack. Let's check the thing we got off the stack is the thing we put on. Let's assert that it's empty after we've pulled it off. Build file 1 error, push stacks undeclared. What did I call it? Oh, why did I do that? Good grief. Good grief, grief, grief. Oh yeah, but I'm going to be writing lots more tests. I don't want to be typing my test stack every time. Okay, there we go. And let's see if it worked. Oop. Clear the log. Let's run it again. Build it and run it again. Okay, so test push, it test is empty, and it test new stack. And they all those tests work. And we should write, similarly, we should write a whole lot of other tests. We should write tests for pop. We should check, you guys think, what a diabolical test should we be testing? What are the corner cases here? Yes? Popping an empty one, oh, well, that'll throw the assert. Because that is a corner case, that's a good corner case. Our pop has as a precondition, and so we're able to assert it, that what it's getting isn't empty. So if someone tries to pop an empty stack, you're dead right, that'll give rise to an error. But the error isn't on part of the people who implemented stack. It's a user error. Yeah, that's right.
Would we just be able to like push everything until like it keep pushing?
Yeah, we should certainly push it right to the end, shouldn't we? So we fill up all 10 and then let's pop it all off. And then check, pop them all off and make sure they're the same in the right push-pop order. And maybe go push, pop, push, pop, push, pop. And maybe push lots of the same values on and see if we can pop the same values off and then push different items and push on diabolical values. Try pushing on some ASCII zeros. See if that's going to make it crash. We just think we do everything mean and nasty we can. Have 2 stacks at the same time. Push everything onto one stack, then pop it off onto a second stack.
And pushing some on one.
Pushing one, some.
Doesn't get any of those.
Yeah, pushing some on one and making sure the other one doesn't mysteriously change. Yeah. Okay, you get the idea. So we could write some ruthless stack tests. All right, now we're going to, let's take a break, because that was an awful lot of talking and typing. Over the break, here's what I want you to think. How could we use a stack, how could we use a stack to write is balanced? You know we've got this is balanced function. How can we use a stack to tell if our brackets are balanced? Okay, let's take a break.